For most of the space age, the search for habitable environments was a search for Earth twins. We looked for rocky planets with atmospheres thick enough to sustain liquid water on their surfaces, orbiting within the narrow Goldilocks zone of their parent stars. We looked for blue marbles in the black void, assuming that life required the specific stability of a sun-warmed surface. But the universe, it seems, has a different and far more abundant blueprint for habitability. We have discovered that the most promising real estate for life in our own solar system is not on the red sands of Mars or the cloud tops of Venus, but in the dark, cold outer reaches, orbiting the gas giants Jupiter and Saturn. Here, beneath shells of ice harder than granite, lie global oceans of liquid water, kept warm not by the sun, but by the gravitational kneading of their massive parent planets. These are the ocean worlds, and two of them, Enceladus and Europa, stand as the most compelling targets in the history of astrobiology. Today, we are going to dive deep into the science, history, and future of these worlds. We will peel back their icy crusts to explore the alien oceans beneath, examine the mechanics of their geysers, and analyze the chemistry that might support a second genesis of life. To understand the significance of Enceladus and Europa, we first need to appreciate the revolution in planetary science that placed them center stage. In the mid-20th century, the habitable zone was strictly defined by distance from a star. Too close, water boils. Too far, it freezes. By this logic, Jupiter and Saturn were frozen wastelands, and their moons were expected to be geologically dead ice balls. But the Voyager missions of the late 1970s shattered this assumption. As they sped past Jupiter, they saw Io, a moon convulsing with violent volcanism. They saw Europa, a smooth, cracked billiard ball of ice with almost no craters. At Saturn, they saw Enceladus, a tiny, brilliant jewel with terrain that looked suspiciously young. These observations birthed the concept of tidal heating. Unlike Earth, which is heated by the radioactive decay of elements in its core, these moons are heated by gravity. As they orbit their massive parents in slightly elliptical paths, they are stretched and squeezed like stress balls. This internal friction generates massive amounts of heat, enough to melt rock on Io, and, crucially, enough to maintain liquid water beneath the ice of Europa and Enceladus. This realization expanded the habitable potential of the universe exponentially. If life can exist in a sunless ocean capped by kilometers of ice, fueled by chemical energy from the seafloor, then habitable worlds might outnumber Earth-like planets by orders of magnitude. Let's start with Saturn's moon Enceladus. It is small, only 504 kilometers in diameter, fitting comfortably within the borders of the United Kingdom. Before the Cassini mission arrived in 2004, it was largely an afterthought. Yet, Enceladus has proven to be perhaps the single most accessible and promising extraterrestrial habitat we have ever found. In 2005, the Cassini spacecraft detected something impossible. The moon was influencing Saturn's magnetic field. Mission controllers lowered Cassini's altitude, and what they found changed history. Streaming from the South Pole were massive jets of water vapor and ice particles, blasting hundreds of kilometers into space at supersonic speeds. These plumes were originating from four massive fissures, dubbed the Tiger Stripes. These are warm, active tectonic fractures, roughly 130 kilometers long. Enceladus was not a dead ice rock. It was breathing its ocean out into space. Over years of careful measurement, Cassini determined that the moon's ice shell was entirely decoupled from its rocky core. The only explanation was a global layer of liquid water separating the two. This ocean is estimated to be 30 to 40 kilometers deep, sitting beneath an ice shell that is less than 5 kilometers thick at the active South Pole. Crucially, the data suggests that the ocean is in direct contact with a porous, rocky core. This rock-water interface is the engine of habitability. As tidal forces knead the rock, water circulates through deep fissures, getting heated and enriched with minerals before rising back to the ocean floor. Because Enceladus ejects its ocean into space, Cassini didn't need to land or drill to sample it. It simply flew through the plumes. The taste test revealed a chemistry that astrobiologists dream of. It found water vapor, salts indicating an alkaline ocean similar to soda lakes on Earth, and organics. Cassini detected both simple organics, like methane, and complex macromolecular organics, which are large carbon-rich molecules. In a pivotal 2015 flyby, Cassini detected significant amounts of molecular hydrogen. This is a smoking gun for hydrothermal vents. On Earth, hydrogen is produced when hot water reacts with iron-bearing rocks. For microbes, hydrogen is like candy. It is a potent source of chemical energy that can be combined with carbon dioxide to produce methane, a process known as methanogenesis. But the most significant recent discovery came in June 2023. Years after Cassini had ended its mission, a team reanalyzed data from the Cosmic Dust Analyzer and found high concentrations of sodium phosphates in the ice grains of Saturn's E-ring. Phosphorus is the P in CHNOPS, the 6 elements essential for life. It is the backbone of DNA and RNA and the currency of cellular energy, known as ATP. Before 2023, we knew Enceladus had carbon, hydrogen, nitrogen, oxygen, and sulfur. Phosphorus was the missing piece. The study showed that phosphorus concentrations in Enceladus ocean are likely 100 to 1,000 times higher than in Earth's oceans. Recent studies published in late 2023 also identified hydrogen cyanide in the archival data. While deadly to humans, hydrogen cyanide is a versatile starting point for prebiotic chemistry, capable of polymerizing into amino acids and nucleobases. Now, let's traverse the solar system inward to Europa, the cracked crystal of Jupiter. If Enceladus is the accessible, eager-to-please moon, Europa is the mysterious, brooding giant. Slightly smaller than Earth's moon, Europa is the fourth largest moon in the solar system, orbiting deep within Jupiter's ferocious radiation belts. Its surface is a landscape of stark, alien beauty, crisscrossed by reddish-brown double ridges that look like scratches on a cue ball. We also see chaos terrain, regions that look like a jigsaw puzzle that has been scrambled and frozen back into a matrix of slush. These are evidence of vast energy from below, possibly shallow lakes of water within the ice shell that caused the surface to collapse and reform. Europa's ocean is a behemoth. It is estimated to be 60 to 150 kilometers deep. Even though Europa is smaller than Earth, its ocean contains twice the volume of all Earth's oceans combined. Magnetic field data from the Galileo mission provided the strongest evidence for this ocean. As Jupiter's massive magnetic field sweeps past Europa, it induces a secondary magnetic field inside the moon, which can only happen if there is a conductive layer near the surface. Salt water is that conductor. One of the biggest questions for future explorers is the thickness of the ice. The thin ice model suggests a shell only a few kilometers thick, while the thick ice model suggests 15 to 30 kilometers. However, the chaos terrain suggests that huge lenses of liquid water might exist trapped within the ice shell, just a few kilometers down. These Great Lakes of Europa could be transient habitats. Europa has also teased us with plumes. The Hubble Space Telescope has detected hydrogen and oxygen emissions above Europa's south pole, and a retrospective analysis of Galileo data showed the spacecraft likely flew through a plume in 1997. However, Europa's plumes appear to be smaller and less frequent than those on Enceladus. Europa has a distinct advantage over Enceladus in one key area: oxidants. Jupiter's radiation belts bombard Europa's surface with high-energy particles, splitting water ice into oxygen, hydrogen peroxide, and other potent oxidants. This surface is effectively rusting. If this oxygen-rich surface ice can be cycled down into the ocean through a process called subduction, it could create a chemical battery potent enough to support not just microbial life, but multicellular life. Just as tectonic plates on Earth dive beneath one another, slabs of Europa's cold, dense surface ice may sink into the warmer ice below, carrying their oxygen cargo to the deep sea. So why do we study both? Why not just focus on the easier target of Enceladus, or the bigger target of Europa? They represent two different classes of ocean worlds. Enceladus has low gravity, meaning the pressure at the bottom of its ocean is relatively low. This makes the ocean floor fluffy and porous, allowing for deep water circulation. Europa has higher gravity, creating immense pressure at the seafloor. However, Europa is larger, so its rocky mantle is likely more geologically active, potentially powering stronger hydrothermal vents. The radiation environment is another major factor. Enceladus orbits in the benign E-ring of Saturn, where electronic systems can survive for decades. Europa orbits deep in Jupiter's radiation belts, where unshielded electronics fry in hours. This makes orbiting Europa incredibly difficult. And finally, there is the issue of longevity. Enceladus is small, and its ocean might be a transient phenomenon. Europa's ocean, maintained by the immense power of Jupiter, is likely 4 billion years old as Earth's oceans. If stability is required for the evolution of complex life, Europa is the better bet. We are currently in the golden age of ocean world exploration. The Europa Clipper spacecraft, launched in late 2024, is currently sailing toward Jupiter. It is the largest planetary spacecraft NASA has ever built. Instead of orbiting Europa, which would be suicide by radiation, it will orbit Jupiter and perform nearly 50 close flybys of Europa, effectively scanning the entire moon in strips. It carries an ice-penetrating radar called REASON that can see through kilometers of ice to find shallow lakes, and a spectrometer called MICE to map the organic and salt distribution on the surface. Europe is also in the game with the JUICE mission, launched in 2023. While its primary target is Ganymede, it will perform crucial flybys of Europa. JUICE has instruments complementary to Clipper, and its focus on Ganymede will provide a perfect control group, comparing a deep ocean world sandwiched between ice layers to Europa, where water touches rock. So what are we looking for? When Europa Clipper, or a future Enceladus probe, analyzes a sample, what constitutes proof of life? It's not as simple as finding a little green bug. We are looking for the Lego bricks of life in specific patterns. Life tends to use a specific set of amino acids and ignores others. If we see a spiky distribution, lots of one type but zero of another, that is a biosignature. Abiotic chemistry produces a smooth bell curve of all possible amino acids. We also look for chirality, or handedness. Earth life uses almost exclusively left-handed amino acids. If we find an ocean full of only left-handed or only right-handed molecules, it is a near certain sign of biology. And finally, we look for isotopic fractionation. Life is lazy. It prefers lighter isotopes like carbon-12 over heavier ones because they are energetically cheaper to process. A sample rich in carbon-12 is a classic sign of metabolic processing. To fully appreciate the complexity of these worlds, we must understand the specific scientific mechanisms that make them tick. Specifically, cryovolcanism and serpentinization. On Earth, volcanoes erupt molten rock. On ocean worlds, they erupt molten ice. On Enceladus, the cold geyser model suggests that the water-filled cracks are kept liquid by intense tidal heating. The vapor speed is supersonic, driven by the expansion of dissolved gases bubbling out of the water, much like shaking a soda bottle. On Europa, the mechanism might be different. A pocket of water freezes within the ice shell, and because ice takes up more space than water, the pressure in the remaining liquid skyrockets until it blasts through the crust. Then there is serpentinization, possibly the most important chemical reaction in the solar system. This occurs when ultramafic rocks rich in magnesium and iron meet water at high temperatures and pressures. The reaction produces heat and molecular hydrogen without any sunlight. This hydrogen can then react with dissolved carbon dioxide to form methane. This simple reaction is the metabolic engine of some of the oldest life forms on Earth. Cassini found methane, carbon dioxide, and hydrogen in Enceladus plumes in the exact ratios that suggest this process is happening right now. The ocean of Enceladus is a giant chemical fuel cell. The study of ocean worlds is not just about finding bugs. It is about the future of human expansion. These worlds contain the three things needed for civilization: water, organics, and energy. While we cannot live on their surfaces due to radiation, we could theoretically build outposts within the ice shells, shielded from Jupiter's wrath, tapping into the thermal energy of the ocean below. As Europa Clipper sails on through the dark of 2026, it carries with it a metal plate, engraved with a poem and the waveform of the word water in 103 languages. It is a testament to our recognition that water is the universal connector. In searching for our reflection in the dark mirrors of Enceladus and Europa, we are taking the next great leap in understanding our place in the cosmos. We are moving from the Earth-centric view of biology to a universe-centric one, where life is not a miracle of the third rock from the sun, but an inevitable consequence of chemistry, heat, and water, playing out on a billion worlds across the galaxy.